Ed Lyon is known for his radio repair workshops that he gives every year at RadioActivity. That's one of the draws that gets some of the people here. And today he's going to talk to you about automatic volume control. And Ed, take it away.
Thank you very much. Okay, this leading slide is supposed to show the sort of thing automatic volume control does. It takes a variable input signal to a radio, like let's say you're in your automobile and you have your radio on and you're driving through a pretty good sized city. And if you didn't have automatic volume control, that is, if it were just absolutely absent from your radio in your car, every time you went between two buildings, you'd probably get a blast of radio volume. And as you went past the building, it may drop in volume, or it may increase in volume, depending upon where the station is and how big the building is and how good a reflector it is. But even in homes, a radio will be affected by people walking around in the room in which the radio is located if it has its own antenna. If it's an old radio and has an outdoor antenna, it's even worse because as the wind blows and the antenna swings back and forth, it changes impedance and it picks up more or less of the signal. So every time the signal coming into the radio changes in volume or in magnitude, it makes the output from the speaker get louder or softer. And in the days before we had automatic volume control, it was really difficult to listen to a faraway station if you were concentrating on what the guy was saying. And I was raised during World War II when everyone was glued to the radio listening for the news because every day the news was different and had something really important to listen to. Not that we could do anything about it, but we wanted to know. So why would I want to talk about ABC? Well, the main reason is I do a lot of radio repair, but not using real tools and not using my oscilloscope and things because I do them on email, primarily on email. People send me problems. There's probably 15 or 20 MAARC members, and some are even not MAARC members, who will send me messages, sometimes one or two every week, with a problem. And in some cases, they're so used to doing this that they send a schematic along with it as another attachment. So I'm at least equipped at that moment to give them a quick answer. So if you have a problem with the radio and you send me a message by email, and my email address is on the page 2 of Radio Age, if you include the schematic or where I can find the schematic in Nostalgia Air or something like that, I will get you an answer right away. Anyhow, that happens quite often, and I usually ask the restoring guy or woman, how's the ABC working? Well, they're not sure. Some people don't know where it is or how to find it, or they don't know what they put a voltmeter on it, whether it's reading right or wrong or what. So we're going to talk about that and what the system really looks like so you can recognize it and you can use for diagnosing exactly what's wrong with the radio. Some people ask, well, does it really replace anything? Does it replace an auto or a non-automatic volume control or a regular knob. No, it doesn't do that. It's about like that 12-year-old kid that was in the living room back in the 1920s when the family was listening to the radio and the kid was riding the volume control. And that was his only job, but he was very good at it. And he did not want to let his 10-year-old brother find out how to do it because he would lose his job. And that job brought a lot of praise from his parents generally. But does it replace anything? No, it doesn't. It is something that the radios did not have many years ago until we invented it. And Hazeltine really walked off with it. So with those two guys in charge, almost every radio from that point on had automatic volume control or tried to have it. Now, some did not succeed, but they left it in the circuit anyhow. And that's another little trick that you're going to find out eventually if you ever fix one of those. This is the kind of reactions I get from most of the, well, not most, but about half of the people who send problems by email, that they want to know, well, how effective is AVC? Well, the bottom number will tell you if the input signal changes by 60 or 70 decibels, that means 10 to the 6th to 10 to the 7th, which is 1 million or 10 million times. That's the sort of variations you get in shortwave, and you also get it in a broadcast band, and it also occurs in your car radio about that big a scale, and that's reduced to something like 10 dB possibly, which is a factor of 10, which is not very objectionable. So that's the value of AVC numerically. It changes a thing that has a very, very variable input signal to something that doesn't seem to have much of an input signal variation at all. So this is the way it works in form. When the signal first arrives in the set, it gets amplified by a number of stages in series. The first stage is up in the RF end of the radio, right near the antenna area. Don't have very much amplification. The main reason is they have to handle a wide range of frequencies. Let's say it's a broadcast set. They have to handle from 500 kilohertz to 1500 kilohertz. That's a 3-to-1 frequency range. And we're asking them to tune in a certain signal over that range and not allow other signals at other frequencies in, or even other signals in that frequency range to get in. So those are amplifiers that have tuned circuits that are variable. And once you make a tuned circuit variable in an amplifier, you reduce the amplifier's overall utility for doing broadband things or to do anything very, very efficiently. So the problem is getting the signal to be amplified uniformly by the radio so it doesn't add to the variability coming in. And one way to do that is to do a superhet. So when the superhet, which most radios are, at least AM radios, when the signal arrives, it gets amplified by a variable frequency amplifier, and then it goes into a fixed frequency amplifier, the IF. And once it's in the IF, it gets amplified quite a bit, usually by a factor of at least 50,000 to 1 million or more. And then it goes into a real simple stage, which is just a diode detector. It's like a crystal set, but it uses a vacuum tube diode. Now, why do they use a diode? Well, because they work well over a wide range of amplitudes. They're really stupid proof. There's no way you can make a circuit that bothers them very, very much anyhow. And of course, in other things in radio, like in radar, they have automatic volume control, but they call it automatic gain control because they don't want you to think of it as a radio. They're much more sophisticated than that. So let's take a look at a couple of real simple radios. I just picked these at random from a pack of SAM. Let's look at the circuits. This is a circuit for one of them, the Emerson 544. And here's the tuned amplifier. Then this is the untuned amplifier. This is tuned, but it's fixed frequency. And so once this stage amplifies and gets changed in frequency, it becomes a fixed frequency in here. So these two transformers never get their frequency changed. And finally, it comes into this diode, which is this little plate and this cathode. And the cathode goes to ground. This is ground, I guess. And that's what the cathode is tied to. So when you have a rectifier that the plate is being excited by the input and you ground the cathode, that makes this part go very negative, just as negative as the peak signal in here as it oscillates. So this gets negative and it passes back through this 2.2 meg resistor. It gets filtered by a capacitor to get rid of any voice signals or music signals that might be on here. And this is the AVC line. And it goes over here into the loop antenna and into this grid number 3. That's actually grid number 3 on the 12VE6, the converter tube. And that grid is a variable mu grid, so that if there's any negative voltage applied to it, its gain goes down. So we have something happening in the way of feedback here. As the signal here gets bigger or smaller because the input got bigger or smaller, that feedback gets bigger or smaller and it changes the gain to that stage just exactly the right amount so that the output is more or less constant. It is still variable, but over a very small range. And in this particular radio I grabbed by chance, there's a thing called QAVC working too. This is a quieting circuit so that as you tune between stations, the gain doesn't go crazy real high because there's no signal coming in. Because if there's no signal coming in, there's no bias going back to cut down the gain. So the gain is full bore. And it'll make a rushing sound. But they did something clever here. Right here, this resistor is very important because that resistor is the bias forming resistor for the local oscillator. And it works all the time, and it has a constant output of about 6 volts. And that negative 6 volts is leaked into the AVC through this 15 megohm resistor, I think it says, or 12 megohm resistor, which leaks a little bit of negative voltage onto that line all the time. So even when there's no station coming in and the gain would have gone crazy, there's that little bit of bias coming in from that local oscillator, which is steady. And that keeps the gain from roaring real loud so it doesn't make a crashing sound as you go between stations. This is the other radio I showed you. And it has a same circuit. It has a pair of diodes. They ground one of them. They don't use it. The second diode is being used. And it goes back and it goes into two grids. It cuts the gain of this one down and cuts the gain of this one down. This is the mixer, and this is the IF amplifier. And they are both variable mu tubes. And we're going to talk about those in a minute. The variable mu tube, which I sketched here, is built this way. There's, of course, the anode is a big cylinder. I've cut the cylinder open. There's a screen grid next. That's this one. Then there's a control grid, which is this one. And the pitch of the wires in the control grid are fine at the ends and very coarse in the center. So it's a real fine thread up here, and it gets very coarse in the center. So what that does is when negative voltage is applied to that grid, and that's the one that gets that feedback, the wires that are close together squeeze off the electrons first. The ones in the middle don't have much effect. But as the voltage gets higher, the feedback voltage gets higher, more and more of these wires get squeezed, or actually squeeze off the electrons. And so finally, after you have like 30 or 40 volts developed of that feedback, all the grid wires are strongly enough excited that they turn off all electrons. And that way the gain of the radio would go to zero. Now, it doesn't really ever get to zero, but it gets very close. The mutual conductance will go from, something in the order of 1,200 micron. No, 1,200 to 2,000 or 3,000 micromoles or microsiemens, down to about 200 or less when you put about 30 or 40 volts on that grid. So that's what the variable mu tube does. And the only tubes that do that are the ones they use in IF amplifiers and in the converter. Now, it has one of these kind of grids. That's that third grid up from the cathode. So who invented that? Well, it was Wheeler. Although others had tried a circuit very similar to it. They were all very, very tentative, but he was very definite what he was after. And so he did it with a real strong purpose in mind and made it a success, even though it was rather simple. And there really shouldn't be any patent on it because it's just the same thing that tubes do. When you put negative voltage on, they shut down. I have another paragraph here, which is interesting. Some of the manufacturers that put basic feedback in use sharp cutoff tubes. Now, why did they use them? Well, they came around before the remote ones were invented, and people had already heard of ABC, and so they installed ABC using sharp cutoff. And the problem there is nothing happens when a strong signal comes in until it gets to a certain strength in it, and then it gets shut off practically. And then instead of just staying off, as soon as it's shut off, the ABC circuit thinks everything has gone sour at the transmitter, and so it turns the gain back up. Then the gain goes back down, and then back up, then back down. That's called motorboating. Now, you probably all heard motorboating in the radio and wondered why it was doing that. And you started applying capacitors all over the place. That's what most guys do. Instead, you check the ABC, make sure it's working, and make sure that they don't have a sharp cutoff tube in there in place of the 6BA6. They could put a 6AU6 instead. It goes in the same socket. and the thing of motorboat for sure. Emerson, they had an interesting experiment, which they ran not intentionally, but one of these experiments that kind of crawls out of the bag and grabs you. They built this radio, and then this is the published schematic. I think this is in Ryder, and he calls it schematic number 1 for this model. And let's see what it has. They have a detector here, which is a triode detector. They do the conversion here in a 6A7. Then they go into a 6D6, which is a remote cutoff pentode. Then they go into a 76, which is a triode. And they do grid leak detecting using a big grid resistor here. And any negative voltage that thing develops due to signals coming in is fed back. So they only go back to this grid and they control it. Now, it did not work. And people complained about it. And they got an awful lot of complaints on this radio, especially from the repair stations. Because everybody took their radio to a repairman, and the repairman always sold a bunch of tubes to them, which is what repairmen do. The damn thing still did the same thing. It just did not work. Now, why didn't it work? Well, because the volume control is one of those old leftovers from the old days that shorts out the signal coming in and also over biases this tube. So it cuts down the gain of this tube and it shorts out whatever's coming in the antenna anyhow. And so that's how they turn the gain up and down manually. The automatic volume control didn't know you were doing that. It has no way of knowing what you're doing in the room. It tried to compensate for anything that you did with that volume control. So people wondered why, when they turned the volume up, it didn't go up. And it didn't go up and didn't go up until they had it all the way up and then it suddenly blasted. So they sent the radio back. It was given back to the same engineer. This is to show what that engineer was thinking. He misunderstood what the purpose of AVC was. He just had heard about it and he saw some circuits. And so he tried to copy a part of one of the circuits and it didn't work. This is schematic number 2. So he changed the circuit. Now he put in a type 75, which is 2 diodes next to the cathode. And that's exactly what modern AVC circuits look like. And he feeds it back to everything. Feeds it back to both the mixer and this thing, but it kept the same damn volume control. So it didn't help anything. It just made it much more intense. This was the result. His boss came in and probably chewed him out and told him to learn what an AVC is before you do any more AVC. So he finally put it in and made it look just like an all-American 5. It looks like any of those other two radios we showed you. They have a regular 6A7, and he feeds back the AVC to this one and to this one, and it worked like a charm. And this radio, they sold a lot of these. That's something I should have mentioned. Go back to the previous slide. Something I mentioned here, it has a bit of delayed AVC. What did I mean by delayed? I didn't mean that it came in a day late or something like that. I meant delayed in volume or in value. And that's a term that's been applied, even though it doesn't mean delayed in time. And the delay is caused this way. They bias this triode with a cathode resistor. That makes the cathode a little bit positive, about 1.5 volts or 2 volts. With the cathode positive by 1 or 2 volts, the first couple volts of IF that come in don't do anything because they don't reach the cathode's voltage, and they've got to be at least as high as the cathode's voltage in order to rectify. It's like taking a type 80 tube and putting big batteries in there to keep its cathode from ever getting negative or anywhere in the ground. It just won't make any B plus. This thing doesn't make any B minus or minus voltage until it gets over this bias voltage. And that's called delayed AVC. It doesn't take over until the input gets over that amount. This explains that in writing, in case you get a copy of these. I want to talk about transistor radios a little bit, even though they don't have any vacuum in them. This is a picture of a 6-transistor broadcast band. I don't even know what brand it was, but it has 2 AGC loops, which we're going to point out. The 2 loops are a diode here that takes the output from this IF transformer and feeds it back an AVC bus, which comes back here, and it changes the gain of this transistor, this amplifier transistor. This is the one after the converters. That's the first IF, or it's the only IF. This diode number CR1, that lowers the gain of the next stage as well. So we have a double loop there for AGC. And it was found to be necessary because you get a very small range of gain changes in transistors before you shut them off. Now, how about FM radios? FM radios don't have a sensitivity to volume, or at least they're not supposed to. So if the input signal changes in amplitude due to driving between buildings or something with an FM radio in your car, the signal gets bigger and smaller, but it shouldn't make any difference in loudness because it's an FM set in theory. But 2 things work against that. One is the discriminator, depending on what kind it is. And this is a regular discriminator here, an Armstrong discriminator, is sensitive to amplitude. It isn't supposed to be, but it is. And as a result, the DFM gets poorer. And so it needs something to help stop that. What they did in this Meissner set is they put a stage in here of IF, which doesn't have any feedback and has no bias. Notice there's no cathode bias and no grid bias. So that's a hard limiter. It accepts only a small input voltage from the stage ahead of it, and it doesn't get any more gain than that. And it doesn't care how big the signal gets, that's how much you get out. And that's caused by the fact that there's no bias on this tube, and it just slams a lid and a cellar on everything. So that's the limiter which keeps amplitude from bothering this detector, which is an Armstrong detector and is somewhat amplitude sensitive. There's another way they could have done that. They could have used an RCA FM detector, which is called a ratio detector. And notice one of the diodes in it is backwards compared to the other. And that's how you can tell that it's a ratio detector. And it is not sensitive to amplitude, so they don't need any feedback or any kind of a limiter circuit. So you save a limiter circuit, and it throws a tube away, and that makes the beam counters very, very happy. This explains that. And it's interesting that there is sort of a feedback loop, and it's paid no attention to by the limiter, and it's also paid no attention to by the ratio detector. So none of it is necessary in an FM set. Most AM receivers use that same diode detector. Here it is, a 6SQ or 12SQ7, and it has a second diode, which comes back and has a 15 meg resistor coming from that same local oscillator. So this is the one that catches the AVC when there's not much signal coming in at all and keeps the gain from going to infinity, or it's a very high number, and makes the set roar or make a loud hissing noise. After about 36, the diode was built into a triode in most cases, and they put two of them in. And someone told the DeWald engineer, we use 12SQ7s for diode detector. We also use them for first audio. So he put two of them in. One to do this with everything else shorted out. The other one to amplify with everything else shorted out. There was a good way to sell an extra tube without designing another tube. And it helps the tube count, which also helps the beam counters. So this is words, and you should take a quick look at it. A consequence to the fact that we use a duodiode plus triode, and that is you can't get cavalier with what you do with that triode. You can't go using its cathode for something else, like putting in a switching circuit or something to do something else, to light a light that means you're tuned in or something. You have to really use it as a simple amplifier, and the best such triode for that is the ultra high gain one, the 12SQ7, which doesn't need any bias at all because it makes its own bias. It robs a little bit of the audio signal, which is the only time it needs bias, and so it makes a fraction of a volt bias, and that's good enough. But it doesn't do anything to the cathode because they earth the damn thing. They tie it to ground. So why did they put two of the diodes in the tube? And anybody have an answer to that? Well, there's an answer here. Of the diode detector, by using the pair of diodes, is at the beginnings of superhits, the IF frequency was something in the order of 18 kilohertz to 40 kilohertz. Those are low enough in value. Those are low frequencies relatively. You can't hear them. A dog can hear part of them. And the problem is that if you use a halfway rectifier like a simple diode, a single diode, you have a hard time filtering out the remaining voltage, IF voltage, because there's always a ragged edge to the output caused by the IF residue. And you have to filter that off with a capacitor. Well, if you put a capacitor that's big enough to filter off that low frequency IF, it also cuts out the highs in the audio. So it affected the audio so badly that they said, well, let's go to a full wave detector, which doubles the frequency, the ripple frequency. And that gives us more room between hi-fi signals of 10 or 15 kilohertz and the IF, which is just a few kilohertz higher. It actually doubles it. So they used a pair of diodes when they first invented this in the type 55 tube, which was the first one that had it. Well, it was not the first one. The first one was a majestic tube. One of those weird tubes with the, looks like concrete on the outside of the glass. The very first dual diode was a majestic. No, but Scott used the 55 to replace the Wonderlic. Oh, yeah, the Wonderlic was invented expressly for full wave detecting. That's all that it did besides audio amplifying. And the Wonderlic, of course, used two diodes, and they were interleaved, so they were perfectly equal to each other. And that made him a very good full wave rectifier. And no one could afford a Wonderlic. So in the next production run of the AW15 radio, the all-wave 15, Scott used a 55 tube just like everybody else. And so there wasn't anything miracle about him. However, that very move that he made to put a 55 in and to use a very good AVC system in the all-wave 55 or in the all-wave 15, and even a better AVC system in the all-wave 23, that cost Zenith a lot of prestige a little later on. So what did everybody do with the second diode? Well, it was just hanging around, so some people just let it hang around. It's like, here's one, this is an Admiral radio. They use one diode for the usual feedback and making the audio for the audio amplifier. And the other diode is just disconnected and left hanging. They do that a lot. At Motorola, they grounded it. They did the same thing, but grounded it. So we just got it out of the way. Another one used it as a clamp to keep this from ever going positive. It's just a diode to ground, basically. This is the anode part. The cathode part goes to Earth. And the idea of that is in case this ever went positive due to a very sharp input signal, like from lightning or some other bolt of electricity, you'd get a loud crash, and that would squeeze that off before it went through this filter. And it would go directly onto the grid as a spike of negative, which would keep it from being so loud in the speaker. You only get a half a spike. Some people ask if hams used automatic volume control. The answer is yes, if they're doing A3, which is modulated signals like voice or modulated Morse. But if they're using Morse code, they should not use AVC. And you can see why. Morse code is just like turning the antenna on or off on a CW signal. And so it makes the gain of the whole system jump to some value for each dot and each dash. And the AVC system will fight that. And it'll make it sound pretty bad. So hams don't use AVC unless they're using A3 modes usually, or they'll use a special AVC that has a fast attack and a very, very slow release. Some radios use amplified AVC. And what does that mean? Well, it means several things to several manufacturers. And Commander McDonald insisted on using it in his pride and joy, of course, which was the Zenith Stratosphere, the 1000Z. And he wouldn't let the guys alone until they had, in his mind, perfected the AVC. And we're going to talk a lot about that AVC because it was terrible. It was the worst thing that they had done with that radio, except for putting 8 6V6s in it. Let's talk about an amplified AVC. There's two schools of thought there. One is using a special amplifier that amplifies the input signal and feeds it back and does nothing but control ABC. It doesn't make any audio. Instead, maybe a little bit different IF chain feeds the audio. So they split the IF into two channels, one that goes through an amplifier to control the input. The other one goes on through to feed the audio amp. And it seems wasteful, and it is, but it's something else for the catalog to brag about. And that's mostly the reason for it. Although it does, in some radios, they can get a much more flexible ABC, which is much easier when the signal is varying clear to off, like in CW, or in case you're going between stations and you really find a blank spot. And let's talk about that zenith stratosphere. This is a block diagram of the zenith stratosphere. Take a look at that. We have there two RF stages, RF amplifiers, and they both use 6D6, which is a remote cutoff pentode. They use a first detector over here, which is a 6A7. So that's a standard mixer. It has a remote cutoff grid, so it gets ABC. Everything in there, that kind of olive red color is what we see. Then there's two IF stages, and they both get ABC. And the second IF stage feeds off a special lead to an amplifier to feed the ABC developer. The ABC developer is a standard diode triode, except for one thing, and we're going to talk about that, which is a rather unbelievable thing. This is what's in that box. Another 6D6, I drew this myself after tracing it. There's a 6D6 amplifier, but its input is not tuned. This is not an IF can. This is just a transformer, a broadband transformer. So it takes the output from the last IF in the radio, and it amplifies it. And of course, any other tracks that might be on it as well. And it feeds it in another transformer, which is also not tuned, but which is biased by a resistor, so it's not very efficient. And it feeds one of these diode plates in the 85. If you look up the 85, it has a mu of about 0, well, a couple, maybe 4 or 5. Pretty low mu too, but it doesn't have much amplification. But it's a cathode follower. Now here they violated that rule that I said, that you don't use the diode triode. You don't use a triode part in a cavalier fashion. You make a simple amplifier out of it and ground its cathode. They did not ground the cathode. They put a 10K resistor. That's the only resistor in the circuit in the B plus line. So it's the only thing where there's any voltage drop, except the tube itself. And that is a powerful low mu tube. It has a mu of about 4. So what happens? As soon as you turn the set on, this point goes to plus 10 volts. Now, what's wrong with that? Well, the AC voltage here has to get over 10 volts before this diode even notices that there's a cathode around. Then it starts to strip off the very tops of that 10 volt sinusoid, and make some ABC voltage out of it, which goes back to the ABC bus. And the only mystery about this circuit is what size these various resistors are. Because this bottom one is a potentiometer, 500 K ohms, which is a half meg. And it has a tap, but we don't know where the tap is. It isn't listed. And so you have to try the tap in different places to see if any of them work. And some of them do work. What happens when this goes to 10 volts is kind of a guess from that point on. Let's look at it rather slowly. Let's say it goes to 11 volts. That means there's 1 volt of ABC formed, and maybe half of that gets back up here and feeds the grid of this tube, and it's negative. So it cuts down the current in the tube. And so this 10K or voltage drop here changes. So this is no longer 10 volts. It's now, let's say, 9 volts. So that 10 volts that was here now makes more than enough to make some ABC. However, the little bit of ABC that it did make shut down the gain of the receiver a little bit. So this may not go back down from 10 volts. The gain might have dropped in the whole receiver and nothing really changed. And it's kind of a mystery what happened because we have no idea what this is supposed to be. So I went nuts trying to figure that out. What I did is I built a stratosphere simulator. This is all the stages of amplification. These are all equivalent tubes. These are their IF cans. These two things, once I finish it, I haven't got it quite finished yet. There's about 12 solder joints yet to make. They bolt together. So this becomes the stratosphere RF section, all the way from the antenna to the second detector. And I'm going to put in place of that tapped resistor, that tapped potentiometer, I'm going to put a 10-turn helipot. Anybody ever heard of a helipot? It's a 10-turn volume control. Pass it around. Why a 10-turn? That's so you can get very fine adjustments. I want to see how delicate that adjustment has got to be to make that thing work. I swear this is a result of the commander coming in after a drunken weekend at another millionaire's place, and where they had a Scott 23 going, and it just pissed him off. And so he said, how dare Scott ever do anything like this, make such a good set with a good AVC system. I want you to double your work on this AVC and make it really sing. Well, I'm afraid it does sing in kind of a Evinrude fashion, like an outboard motor. So this is a little text slide, and this explains what I just said about what was going on with that so-called AVC amplifier. They made a cathode follower out of it, and that was probably a big mistake. So this explains exactly what I just went through. And if you get a chance, get the schematic out for that radio and take a look at that. First of all, I dare you to actually find your way through it without getting lost a couple times. It is really the worst looking schematic I've ever seen. Looks like it grew like Topsy. And this explains why I'm a little bit irritated about that set. Okay, so let's go back and look again at that circuit. I want to make sure everybody understands what we had there. And that shows that same schematic again. And if you get a copy of these slides, which any of you can get from me by emailing me, I'll send you a copy by email. Or we'll put it on our website, either one. And you'll be able to do your own calculations with this thing and write all over it. So anyhow, this is my explain about it, my explanation. And I'll tell you one other thing that we did with this circuit. Joe Sousa asked me if I had seen it, and we were talking about a different radio at the time, but this one came up. I think it had to do with the issue of Radio Age that had a big article about the stratosphere, and he had done a simulation of this circuit using a modern simulator, which of course did not look at any of those same tube types, but that he looked at similar tube types. And for the cathode follower, he couldn't find any simulation for a cathode follower using an 85. So he used a 6SJ7 with all the grids tied together to the plate, or to the control grid, I guess. Or some of them to the plate and some to the control grid, made a tryout out of it. And that seemed to work fairly well. But he also found out that that tap point in that resistor is very critical. But we haven't yet zeroed in on just what values it has to be. So if any of you have a stratosphere and it's acting up, it could very well be that ABC circuit. So this explains what my complaint on about it was. This is Joe's simulation. And like I say, it could end up being an Evinrude imitator when you put the wrong size resistors in there, or the wrong place in that tap pot. Or if you can't get a tap pot, what do? You put two resistors in, but what size do you use? So we have another picture of that thing going. That explains the simulator that I built. I'm going to try to finish this thing up in time for the July newsletter. And if I don't make it in the July newsletter, there'll be an article on ABC in the July newsletter, and this will be in the September newsletter. Some results of the tests on that thing. Anybody got any questions about ABC? Now, when you're servicing radios, what do you do about the ABC? Well, when you're aligning the IFs, for example, you should short out the ABC or set it at some low voltage. A good way is to use a 1.5 volt battery with a couple of clip leads soldered to it. Now you have to use a battery that you're not going to use for anything else. And you bias the ABC circuit by about 1.5 volts and let the radio work on that while you're doing the alignment. Now, why do you do that? Well, I have that on this scope. So if we can move this camera around, Joe. What I wanted to show you here is this. I have a signal generator here, and it is producing about 400 and some kilohertz right now, 450 or 460. And I have an IF transformer in it with the top trace, the B signal, this one. This is the input signal coming from the signal generator. And this is coming to the primary of the transformer. I have them all clipped together here. And as I change the frequency, Notice the primary goes to a maximum at this point, whereas the secondary goes to a maximum at this point. So this thing is mistuned in either its primary or secondary by a very small amount. Now, if it were a huge amount, you'd see the primary peaking up at one place on the dial and the secondary somewhere entirely different on the dial. But this thing came out of the box, tuned just like that, and looks like the primary is very slightly higher in frequency, a little lower in frequency than the secondary. The secondary reaches its maximum right here. The primary reaches it right here. So if you can read those points on the dial, it looks like it's about 20 kilohertz. So this needs to be tweaked, and the way you tweak it is with a brass screwdriver, which can reach those powdered iron slugs they have inside these little cans. Now, here's a regular size IF can I removed from something many years ago. We can slip it in place of this one, and you can see what its tuning looks like. I don't know if it was tuned completely before it was removed from the radio or not. I want to show you how we outfit scope leads. First of all, you should use a tube input scope, just like this one, or something similar. It's a lot handier because you can put one on the primary and one on the secondary. They're colored, one has a red collar, the other has a blue collar. Switch them over to here to which channel is which, and one of them works the A channel, and the other one works the B channel. So what we'll do is we'll put the B channel, that's the blue trace here, on the primary of this transformer. And the primary is usually a red and blue lead, which look like these two right here. Now, to find out for sure, I would use an ohm meter. Find out which is the secondary. Very good. So as I was saying, we're going to put one of the scope traces on the primary, A trace on the primary. So we fasten the hot lead to the primary and the other one to the one that went to B plus originally. And we have over here the secondary, and we'll use the secondary to measure what's going on in the secondary of this transformer. So we put it across the secondary leads. I have nothing coming into the thing and nothing going out, so everything is quiet. We don't have any unusual signals in this room. But here I have a signal generator, and first thing I'll do is fasten its ground to the same ground as the scope uses, and I'll feed its input to the primary. Now, I don't feed it directly to the primary. Why don't I feed it directly? Well, if you feed it directly to the primary with this clip lead, it keeps the primary from ever changing voltage, so you can't tell if the primary is tuned or not. So what we do is we insert a resistor in series with the lead from the generator. And I have it already on this generator, and it turns out to be a 27K resistor. And that's probably a good enough size to use, 27K, maybe 47K, somewhere in that region. And we'll insert that on the primary, which goes to the blue lead, that goes to the plate, just like that. And so we have on the A lead, which is coming into the primary, that signal, and the B looks like we have nothing, because what did we do? We don't have either I don't have this on B plus. See, without an ohmmeter, I can't tell which leads are which of these things. And notice my hand takes the signal away, like my body does. Something is amiss with this wiring. These color codes are probably not very distinct. This is a 50-year-old. This is a 50-year-old transformer, which
May have given up the ghost.
it may have an open secondary. We'll go back to this one, which is a brand new one out of the box. By brand new, I mean it's only 25 years old or 30 years old. Because the box is about that age. But we all saw how it worked, and it was rather straightforward. So this is back to that same picture we had originally. The primary and secondary are slightly off from each other. It's an easy problem to fix this one. You just have to use a brass screwdriver. Why brass? Because it uses magnetic material. It uses a magnetic material for the tuning. Uses a slug of oxide, and it is self-magnetic, so you have to use a non-magnetic tuning device. You use a plastic screwdriver, but many of them twist off and leave bits of plastic inside the can, which you have to then take out. So it's a simple thing to use a two-trace scope to check IFs, and you should do that with the AVC system fixed at some voltage. You can go ahead and put a short circuit across it, but that's 0 voltage. And if you have one of these systems that has the little bit of leakage from the local oscillator grid to keep it from making roaring sounds between stations, you don't want to short that out completely. So the best thing to do with the AVC line is to put a slight negative voltage on it, like 1.5 volts from a battery. Make sure it's negative 1.5 volts onto the AVC bus compared to its local ground. Now, most of the time, if it's a very high quality radio, that'll be the chassis. If it's a AC/DC set, you better use an isolation transformer because it's very close to being the power line. In fact, it may be connected to the power line. So you have to be very careful with your test equipment in a case like that. Always use an isolation transformer. Okay, any questions? We're all through. We talked about AVC. You have any questions about AVC? No? Good. Thank you.